Okay, so let's read the first problem. Do you all have it? I have some copies of set 21 if you need it. So the body consists of a uniform slender rod and a uniform disc. So it's a full disc, it's not a hoop, it's a disc. Each of mass m/2. It rests on a smooth surface. Determine the angular acceleration alpha and the acceleration of the mass center of the body when the force P equals 6 newtons is applied as shown. The value of the mass m of the entire body is 1.2 kilograms. So m is 1.2 kilograms. We want to determine alpha and AC. Notice when I wrote the dimensions, I directly wrote them in SI. It's a common problem with these kinds of problems is if you don't convert the units to SI directly, then you might run into trouble later on, because what you're doing is you're taking, when calculating the moments of inertia, for example, you're taking the square of distances and so on. So then later on you will have to like convert the square of the distance instead of just the distance. So my advice is in these problems directly convert to meters if you're doing SI, or feet if you're doing US units directly from the beginning. Okay, so the uniform body consists of the rod and the disc, each of mass m/2, and the force F is applied as shown. We need to determine alpha and AC. What do we do? Maybe take a minute, discuss with your neighbors, try to come up with a strategy. How do we solve this problem? Or just simply, where do we start? How do we start? Okay, any ideas? What do we do? Any ideas? How can we start? What equations are we going to use? Well, the start is easy. How do we always start? Yes, we're going to do the 4 steps. We already have our basis. We'll see about the origin. We're going to take it here, not on the rigid body, because there is no fixed point on the rigid body. The free body diagram. Before the free body diagram, if we're still in step 1, we want to calculate the center of mass of the rigid body and the moments of inertia. Do you think we're going to need to calculate the center of mass of the rigid body? We have some disagreement. So let's start with the free body diagram, continue, and we'll see if we'll need to calculate the center of mass, the location of that or not. Okay, so if I draw the free body diagram of the rigid body, I have to isolate the rigid body. Already no supports are attached to it. What are the forces acting on the body? The force P. What else? So the P is some force along EX. Are we given the magnitude of P? How much is it? 6 newtons, okay. What else do I have? Weight force. So there's going to be some center of mass of the body, and the weight force is acting into the page, passing by the center of mass, right? What other forces are acting on the body? Normal force. So the weight and the normal force are both along EZ. Okay, great. Anything else?
Shouldn't P be along EY?
Yes, along EY. Thank you. Anything else? Any other forces? I think that's it. Okay, then what do we do? We want to calculate alpha, the angular acceleration of the rigid body. We're going to use the balance law, right? Which one? Balance of angular momentum above the center of mass. Yeah, that makes sense. We're going to use MC, so the balance of angular momentum. MC is equal to H dot C. Okay, could I have applied MO is equal to H dot O? No, why not?
There's no fixed point.
Exactly, there's no fixed point on the rigid body. And then MP is equal to H dot P plus the other terms. I could have applied the sum of moments about P or. But let's stick with this one about the center of mass. Seems simpler. So then I need to calculate the moments of the forces. What is the moment of the weight and the normal force above the center of mass? 0, right? So I still need to calculate the moment of the force P. So the expression of that is, let me call this point A. RA minus RC cross PEY. Is that correct for the moment of the force P? Raise your hand if you agree. Awesome. Any other moments, couples I need to put? Or that's it? I think that's it. Okay, and H dot C, then it's this expression here. I x z alpha, here it's about the center of mass, minus I y z c omega squared plus I c. Okay. So now what do I need to calculate? The inertia terms. So I see okay. Are the products of inertia 0 in this problem? Or are they non-zero? Take a couple minutes to discuss with your neighbor. Are the products of inertia 0? Are the products of inertia equal to 0? Yeah, and let us take a rotational basis like that. Okay, so what do we think? Are the products of inertia equal to 0? Raise your hand for yes. Raise your hand for no. Okay. Why not? I think maybe we'll have to go through the detailed calculations. So before we do that, we'll have to find the location of the center of mass. So let's first find the coordinates of the center of mass, the position vector of the center of mass. Okay, so we have this body. Actually, I want to find RC with respect to A. So I have my center of mass C, my point A, and I want to find this distance, RC with respect to A. So this body is composed of the rod or the bar and the disk. How do I find my center of mass? C. Yes. Right. So I have to think of the center of mass of the bar, C sub B, and then the center of mass of the disk. So RC with respect to A is the mass of the bar, which is m over 2, times R CB sub A, plus the other m over 2, R C of the disk with respect to A over the total mass m. Do we see what we did here? It's the sum. The formula for our center of mass is RC is the sum of mi Ri over the sum of mi. Or even if you consider the integrals, RC is the integral of R dm over the total mass. So that's mRC, basically, over the body. And we divided the body into two. The integral of over the bar of R dm plus the integral over the disk of R dm. So that's just the mass of the bar times the center of mass of the bar plus the mass of the disk times the center of mass of the disk. And instead of taking my origin to be O, I can take it to be A. So I can say does that make sense? Okay, what is this vector? The position vector of the center of mass of the bar with respect to A. What is that equal to? So what is this vector equal to? We have all the dimensions, right? We have the coordination basis vectors. What is this vector equal to? What is it? 0.25 along which vector? Okay, great. So that I don't get confused with numbers, what I will do is I will name this length L and this the radius here R. Okay, just to make it easier. So L is 0.5 meters and R is basically 0.1 meters, half of the diameter. Okay, so then this is equal to 1 over 2. I'm going to divide m. L over 2EX, correct? What's the second one? In terms of R and L, that's equal to what? Raise your hand if you agree with this. Okay, cool, awesome. So this is my position vector of the center of mass. Great. Now I want to find the moments and products of inertia. Let's start with the products of inertia. IC XC of the whole body is ICXZ. I'm going to divide the body into two. The bar plus the disk. Of the bar plus ICXZ of the disk. Okay? Now, let us find each one of these products of inertia on its own. ICXZ of the bar, well, if I look at the tables, can I find the moment of inertia of the bar about a point that's here at the center of mass of the system? In your tables, maybe open up the tables. Yes. So first, let's answer the first question. Can we find in the tables the moment of inertia of the bar about this point here, the center of mass of the system? No. So what are we going to use to find that this term? The parallel axis theorem. So that I see about the center of mass of the bar, which we have in the tables, xc of the bar, plus the parallel axis theorem, which is equal to minus m of the bar, a x az of the bar. So what is the product of inertia Ixz of the bar about its own center of mass? No, that's the product of inertia. You said the moment of inertia. I want the product of inertia. Yes, it's 0. Why? Because that is equal to minus the integral of xd dm, xd position vectors from the center of mass. And we argued last time, because of symmetry, this integral is equal to 0. Okay? Now for this one, what is ax, az of the bar? These are the components of the position vector from which point to which point? The center of mass of the bar to the center of mass of the body. So what is the z component of this vector? 0. So what is az? 0. So that term, all of it is 0. Now please do the same thing for the other term. Is it going to be 0 or not? For the disk, is that product of inertia xc going to be equal to 0? Okay, let's give it a few more seconds. And if you're done with that, maybe check the other product of inertia ICYZ. Is that going to be 0 or non-zero? Okay, so what do we think? Is this term going to be 0? Raise your hand for yes. Raise your hand for no. We still have some undecided people. So the idea is the same. We're going to do the same parallel axis theorem. ICD XC of the disk minus M of the disk, AX of the disk, AZ of the disk. What is this term for the disk? The product of inertia XC about its own center of mass. It is 0 also because of symmetry. Remember, the EX, EY plane is a plane of symmetry here. And also AZ is 0. So that's 0. So this term is going to be 0. If you do the exact same calculations, the other product of inertia, IC, YZ is also going to be 0. Any questions? Questions? Okay. You'll be doing this on your own in a bit, so if you have any questions or if you need me to do it again, please let me know. Okay. Now what we need to find is the moment of inertia, ICZZ. And that's going to be non-zero. ICZZ is ICZZ of the bar plus ICZZ of the disk. Again, we do not have this in the table, so we're going to use the parallel axis theorem. ICZZ of the bar, using the parallel axis theorem, is IC of the bar about its own center plus AX squared plus AY squared. Okay. From the tables, what is the first term? The moment of inertia, not the product of inertia, the moment of inertia, ICZZ of the bar about its own center of mass. And the axis is perpendicular to the bar. Z is perpendicular to the bar. So what is that equal to? 1 over 12 ml squared. So 1 over 12, the mass of the bar is m over 2. The length of the bar is L squared. Does that make sense?
Yes.
Okay. And then the mass of the bar is m over 2. What is AX equal to? Yeah, that's a little bit tricky. Think about it. Chat with your neighbors. What is this AX equal to? AY is 0, so the other one is easy. AX, what is it going to be?
L plus 2R
Okay. So I know that this distance from A to the center of mass is equal to what? This one is AX, right? This distance from A to the center of mass is what? Is the RC projected along EX. So that's equal to, I can simplify this. Simplify this a little bit. So that's L over 4 plus L over 2, 3L over 4 EX plus R over 2 EX, right? So that's going to be equal to 3L over 4 plus R over 2. And I know that this distance is what? From A to CB, L over 2. So I can find AX as the difference of the two. So AX is going to be equal to 3L over 4 plus R over 2 minus L over 2, which is L over 4 plus R over 2. We need the extra parentheses. Right? Any questions? Now work on ICZZ of the disk. The moment of inertia of the disk above the center of mass of the body. Take 2 minutes, please work on this. The moment of inertia of the disk above the center of mass of the body. Mm-hmm. You can think of EX and EY. It's a plane of symmetry of the body. If it passes by C or CB or CD, the EX EY plane is still going to be a plane of symmetry. So that's how you know that the integral is going to be 0. So the product of inertia is going to be 0. What is it? Yes, and then the rim is, and the smokes are like almost massless in comparison. Okay, so what do we think? Let's take a vote. Who thinks that wheel A is gonna arrive first? Raise your hand. Is gonna arrive first. Seems like we have a consensus on A. Why will A arrive first? Yes. Exactly, exactly. So if I look at for A, the moment of inertia about the center of mass, ICCZ for A, that's equal to what? The moment of inertia, the mass distribution about the center of mass, the z-axis passing by the center of mass is what? So what is ICCZ for A? We're looking at the mass is all distributed, it's all concentrated along the z-axis. So then what is the mass distribution about the z-axis? If it's all concentrated on the z-axis, it's 0, right? Whereas for B, what is ICCZ at A? ICCZ for B, the mass is all equally distributed from the z-axis. If I want to integrate x squared plus y squared dm, all the masses is, or the mass is equally distributed at a distance r from the center of mass. So that's equal to r squared times the total mass, mr squared. So the moment of inertia for A is much less than for B, meaning that our resistance to rotation is less at A, meaning that A is going to have a more angular acceleration, is going to arrive faster. If I apply my balance law, this one, MP is equal to H dot C plus RC minus RP cross M AC. If I apply this equation, or even if I apply the MC is equal to H dot C and F equals MAC, then I can solve for the angular acceleration alpha. And I will see that the fact that ICCZ is 0 makes that this one arrives first. Shall we do this problem? Shall we solve it? Yeah? Want another one? Yes. Right, so to find ICCZA, that's the integral over the body of x squared plus y squared dm, right? Where x and y are the distances of my differential mass dm from the center of mass C. But all the mass is concentrated along the center of mass. So then these are 0. Okay? The mass is all concentrated at the bar, so there's actually no mass distribution above the bar, kind of thing.
So you don't use
the tables. You could use the tables.
Well, you don't use the one for the bar.
Right, but you have to be careful. You're using the one for the bar, but here the axis is along the bar.
Right.
So you're looking at the mass distribution from this axis. So you look at the particle and at the distance from the axis, which is almost 0 because it's a slender bar. Does the table give you a value for this?
It has the cylinder one.
For the cylinder, what is it?
1/2 mr squared.
1/2 mr squared. But then if r is 0, you get 0. Okay, great. Okay, let's do our quiz. Let's aim for 30 minutes, and if we have extra time, if you finish by 30 minutes, then it's great. Then we'll solve more problems. If not, maybe I'll give you some extra time. Let's aim for 30 minutes for the quiz. It's actually a fixed point rotation problem. Here you go. Put all your electronics away, please. I'll give you a formula sheet and a question.